Okay, so the explanation for the fact that we get just blue, red, and purple coming out, I don't know why that resized here, is the Bohr model. So we're going to look to see what is this Bohr model? What are we talking about with the Bohr model of the atom? Let's scroll down a little bit. They also show that's called a line spectra, when you see the different colors coming out of a particular discharge tube like that. That's called the line spectrum. This just happens to be the line spectrum for hydrogen. These three colors that we saw here is just for hydrogen. Other elements would have different sets of colors coming out. So helium has a blue and a purple, like hydrogen has. It's got a red, like hydrogen has. Not exactly in the same place, but it's also got a yellow, which hydrogen doesn't have. And it has an orange, which hydrogen doesn't have. So helium has a more complicated spectrum than hydrogen. Hydrogen has one of the simplest spectrums in the visible, and we'll see why in a minute. Barium has even more colors than that. Okay, so barium has all these different colors in it that are emitted, and all of these colors represent individual, really they're particles of light that are being emitted. Now, what they show down here at the bottom is this is just a rainbow of colors. It's all the colors that you could possibly get in the visible spectrum, visible part of the spectrum. So why do we get these different line spectrum for the different elements? Well, here's the explanation. It's the Bohr model of the atom. Bohr model. So the Bohr model of the atom says that electrons orbit the atom at certain fixed energies, which means also certain fixed radii, certain distances from the nucleus. So each of these lines right here, first, this is the nucleus of the atom, right down here, this is the nucleus. And then each of these lines represents an orbit that the electron can have. So imagine this first line right here has it represents an electron that's moving in a circle, going around the atom in a circle like that. And then the next one represents another electron. Here they have a picture of it, and the electron here is also moving in a circle. This next line also can represent an electron that's moving. So each one of these circles is just that. It's representing an orbit for an electron, but at different distances away from the nucleus. All these are different distances. Now, how does that explain our spectrum? Well, that's what they're trying to show here in this picture. It's kind of a complicated picture. So let me try to explain it using some help here with the drawings. So one of the colors that you saw in the hydrogen spectrum was this red, right? Red is a low energy compared to blue and violet. Okay, so violet up here is the highest energy. So red is the lowest energy. Low energy. So that corresponds to a light that has less energy than violet does, because violet's a higher energy. Higher energy, okay? And we already mentioned that in looking at the electromagnetic spectrum. Well, why is there a low energy one and a high energy one and not anything in between except for this other kind of bluish color right here? That's kind of in between. Well, it's because of transitions between the orbits in the atom itself. The red color corresponds to an electron going from level 3 and dropping down to level 2. And when it does that, it emits light that happens to be red. It emits red light with that transition. For another electron that might be way out here, starting at level 4, when it drops down, it can also drop down to level 2, but when it does that, it emits sort of a bluish color when it drops down. It also emits light, but that light is blue because it's a higher energy. The bigger the transition, the higher the energy that's going to be emitted because the electron is giving up that energy. So when you have a small gap from 3 to 2, that's less energy than that bigger gap from 4 to 2, which is less than the even bigger gap from 5 down to 2, which is where you get the purple. So with this, when it goes from level 5 down to level 2, okay, that's the biggest energy change that it has, and that's where you get the purple. Okay, so all those things, those are called emission lines. So this is emission. And that's what's happening in that gas tube. Now, the reason why it has to be hooked up to an electric current for it to do this is because the electrons, they don't really like being way out here in these other orbits. If left to their own devices, if they were just left alone, the atoms would all have their electrons in the very first orbit, the n equals 1, because that's the most stable condition. So if we didn't have electricity hitting the atoms, all the electrons would just instead be right down here. And there, remember, hydrogen only has one electron anyway. So there's just one electron, and it's very happy to be down here closest to the nucleus. Now, it can't get completely close to the nucleus because otherwise it would crash into the nucleus. So it has to have a minimum radius, and that's the n equals 1. But if an electron, if it's excited, if energy comes in and bumps it up to a higher orbit, then it's going to be in that higher orbit. Let's say bumps up to here. Okay, that would happen because of electricity hitting it. Okay, so yeah, electricity causes that. At least in a light bulb, in a fluorescent light, it's an L. Electricity is what causes this to bump up. But then when it drops back down to level 2, it emits that purple light. But a different atom might have its bumped up just to level 3, and when it drops back down, it would emit red light. So you have all these different transitions going on as the electricity is bumping into all of the atoms of the hydrogen that are there. And that's how those lamps work. That's how fluorescent lamps work too. Now, why do you need the Bohr model here? Well, the Bohr model, what's unique about the Bohr model, and this is a huge breakthrough, is that these orbits of the electrons are what's called quantized. Okay, or fixed. they have certain values that they can have, certain energy values and certain radii that they can have, and they can't be anywhere in between. So in other words, I can't just stick an electron orbit right there. So if I wanted to put an electron here, I can't do it. That's not possible because that's not one of the possible orbits. So this wouldn't exist. Okay, that orbit wouldn't be there. There's only certain ones you can have, and those certain ones are labeled. Each orbit is labeled with a number, and that number is designated by the letter n. You can have n equals 1 for the smallest orbit. You can have n equals 2 for the next bigger orbit, n equals 3, n equals 4, n equals 5. And then they keep going on from there. You just get bigger and bigger orbits. So the Bohr model has that idea that those orbits are quantized, and the labels for those orbits are the value of n. N is called principal quantum number. That was a lot. You guys have any questions on that? It's all in that one graphic, really. That's the Bohr model of the atom, and that explains why some atoms have different color combinations than others, because the values for these orbits are different depending on the atom. All these different orbital levels change depending on the atom. So that depends on really the element. Where these orbitals are depends on the element. So you might have some elements where these levels are closer together, and so you get more smaller, like the lower energy levels, and then you can get a lot more lines as well if they're closer together. So that gives you the different line spectrum, like we saw before in that previous picture. Like this one, this is oxygen. Oxygen has a ton of different lines in it because all those. Well, not only because the orbits are close together, but because there's a lot of electrons in oxygen that occupy those orbits. So you have transitions not only down to the n equals 2 level, but you have transitions between the orbits that are higher than the n equals 2. And same thing with neon. The more electrons you get in an atom or an element, the more lines you're going to get like this. This just shows the some elements, what colors they have, but you have to remember that each of these colors, like you have here, that represents all of the lines together. Like this purple is made up of different colors, and the red here is made up of different colors combined to form red. I'm not sure what color that is. Green, I guess, kind of got a greenish to it. That's also the basics for fireworks, is that all these elements, when they burn, give off overall different colors, and then you can mix different elements in fireworks and get all these different colors. You can also have absorption spectrum. So emission spectrum is where the light is being emitted. Absorption spectrum is when you have light that's passed through a sample and the atoms absorb only particular wavelengths, and that's wherever you'd have a bright line up here, you have a dark line down in the absorption spectrum. Okay, now that's not the end of the story, because the Bohr model of the atom doesn't explain everything. It's very good at explaining what happens in hydrogen, but it doesn't explain what happens when you have more than one electron in an atom. You get variances that can't be explained just by the Bohr model of the atom. And so that's where quantum mechanics come in. And section 4 is really giving you an introduction to quantum mechanics and the quantum mechanical atom,